Equipped with a domestically produced 2,000 horsepower engine and dynamic brakes, the DE50 was born as a culmination of JNR's diesel locomotive technology. Featuring a high-power single engine and a large hydraulic transmission, it significantly reduced maintenance costs for the power unit. The addition of dynamic brakes was expected to reduce brake shoe wear on freight cars, thus lowering operational costs for freight transport on local main lines plagued by deficits. Despite concerns over the DE50's 10% lower output compared to the 2,200 horsepower DD51, it was anticipated that the DE50 could handle the operations with its 14-notch control, as many freight trains operated under 12-notch schedules with the DD51. During a time when long freight trains were rare on non-electrified lines, the focus was on labor saving and maintenance cost reduction, driving the demand for a new generation of locomotives. The DE50's 5 driving axles increased effective adhesion weight compared to the DD51. Additionally, all driving axles were connected via cardan shafts, reducing the likelihood of wheel slip, allowing for smoother operation under adverse conditions where the DD51 struggled. The transmission system of the DE50, like the DD51, used a 3-stage gear shifting method controlled by 3 hydraulic transmissions. The system included a fluid coupling for dynamic braking, making it JNR's first integrated transmission system. A high-capacity transmission was required for the first gear to endure long periods of low-speed heavy loads. For the second and third gears, traditional single-stage 3-element converters were used. But for the first gear, a 3-stage 6-element converter was attempted but abandoned due to cavitation issues. Without the ability to measure stall torque due to equipment limitations, concerns about low-speed tractive effort remained unresolved during tests. However, it was critical to address this issue as freight hauling on gradients with small-output diesel locomotives required long periods of low-speed full-power operation. The oil cooler capacity for the transmission was designed to dissipate heat generated by the fluid coupling's dynamic brake, allowing for 1,600 horsepower absorption at the 7-notch dynamic brake setting. The DE50 underwent various tests from the summer of 1970 on the Shinonoi Line, Chua West Line, Sanayo Main Line, and Hakubi Line. The vehicle strength and vibration test car, Suya 11, was coupled to collect and analyze various data. Suya 11 was equipped to measure and analyze displacement, wheel load, lateral pressure, derailment coefficient, temperature, pressure, and hydraulic pressure, among other parameters. Structurally similar to the 12 series passenger cars, Suya 11 had observation windows on the sides, reducing the car body width. To ensure stability at high speeds, the center of gravity was set at 1,265 mm with a lateral deviation of 3%. The bogies, similar to Shinkansen EMUs, were designed to support speeds up to 150 km per hour. With the commencement of 110 km per hour operations for passenger trains, the high-speed braking system was equipped with disc brakes. 2 of the 4 axles had spoked wheel centers to measure wheel load and lateral pressure. The brakes also incorporated disc brakes to support high-speed operation. This structure was similar to that of the trailer cars in the 103 series EMUs. And the brake shoe linings were made of the same material used for express EMUs. The measurement equipment installed on this vehicle was also state-of-the-art, including pulse generators, inkjet oscillographs, AD converters, teletypes, industrial television equipment, slip rings, dynamic strain gauges, temperature recorders, and magnetic tape recorders, all of which were state-of-the-art at the time. For these devices and air conditioning, the same power generation set as the Kiha 65 was installed. To meet the high stability requirements of the measuring equipment regarding power supply frequency and voltage, a dedicated inverter was used, making this measurement vehicle a pinnacle of JNR technology. The high-speed running characteristics were investigated on the Sanyo main line and Hakubi line, with the 3-axle bogie positioned on the downward side. Although tests up to 110 km per hour were planned, only measurements up to 105 km per hour downward and 108 km per hour upward could be conducted due to strain gauge malfunctions in the wheel load measurement. The high-speed stability of the 3-axle bogie, although showing oscillation in the leading axle, did not deteriorate at high speeds and was deemed acceptable. Tractive effort characteristics were examined on the 25 per mil gradient sections of the Shinonoi line. 2 types of trains were planned, one with a load of 520 tons for testing the performance of the first stage converter, achieving a balanced speed of 20 km per hour, and another with a load of 330 tons for testing the second and third stage converters, achieving a speed of 32 km per hour. The initial test, with an actual load of 556 tons, faced difficulty in pulling out from the gradient, needing assistance from the coupled DE51, and could not reach the planned speed, leading to the test's suspension. The starting tractive effort was only 18.4 tons, significantly below the planned 21 tons, with no wheel slip observed. Even at full throttle, the balancing speed on the same gradient reached only 14 km per hour, with a transmission stall-torque ratio of 2.6, causing the engine to operate in an overloaded state. The second test, with a reduced load of 472 tons, managed to start but showed a balanced speed of 20 to 21 km per hour on the 25 per mil gradient, 2 to 3 km per hour lower than planned. Tests conducted 3 times on gradient sections showed no wheel slip even under full notch operation, indicating that performance degradation at low speeds was due to the first stage converter. The second and third stage converters performed as planned, highlighting the need to improve the first stage converter. During the 14-notch operation, the engine ran at approximately 1490 rpm, with a fuel consumption of 425 liters per hour and an exhaust temperature of about 600 degrees Celsius, consistent with the plan. While the main cooling water flow was sufficient, the intercooler cooling water flow was found to be inadequate. The cooling performance of the engine, intercooler, and transmission was generally satisfactory, but concerns arose about high exhaust temperatures and the recirculation of radiator heat in tunnels, particularly regarding the intercooler's cooling water pump, necessitating improvements. Regarding dynamic brakes, descending a 25 per mil gradient with a load of 272 tons at the highest setting, 7-notch, did not suffice to maintain the speed limit of 50 km per hour, requiring the use of air brakes. For a load of 128.6 tons, balancing was achieved at about 35 km per hour with 7 notches and about 40 km per hour with 4 notches. The fluid coupling absorbed 1300 horsepower, with oil temperatures rising to 96 degrees Celsius. Considering the summer ambient temperature, the significant temperature difference between the inlet and outlet of the hydraulic fluid cooling system indicated insufficient cooling performance, necessitating an increase in transmission oil flow. Variations in braking performance due to hydraulic oil temperature and air bubbles affected dynamic brake torque, resulting in lower than planned values at the 7-notch setting. The allowable absorption horsepower from the radiator's performance was 1,600 horsepower, but with the transmission oil temperature exceeding the limit of 115 degrees Celsius, increased coolant and oil flow were needed. Furthermore, expanding the control valve air passage successfully shortened the air brake release time. However, when DE50 operated as the primary locomotive with DD51 as the auxiliary, the brake release delay on the DD51 side remained an issue requiring improvement. Overall, the high-speed characteristics of the unique AAA axle arrangement bogie were satisfactory, but the first-stage converter's performance shortfall emerged as a key issue, necessitating its improvement. Additionally, research began on using water instead of oil for dynamic brakes to significantly increase capacity. However, during these considerations, the environment surrounding JNR diesel locomotives underwent rapid changes. The oil crisis led to soaring fuel prices, increased dependence on nuclear power for domestic energy, and further pressure for railway electrification. With JNR facing severe financial deficits, the demand for powerful engines became uncertain. The high-output engine, expected to deliver 4,000 horsepower with 2 units and making the dream of hauling 1,500 tons a reality, was considered to finally match world standards. Although there were applications outside of railways, such as emergency power sources and pump drives, the suspension of the DE50's development meant it never found a role in locomotives.